I'm so verklempt. Okay. I want to try and solve this one. The problem I have is that x equals 0 is singular. So I need to ask the question from yesterday, what kind of singular? What kind of singular point is x equals 0? Yeah. Yes, if you're guessing, but you should be able to tell. It is regular. How do I know?
X cubed. Is it x squared?
Yes. X p of x is an eighth. X squared q of x is x over 4. And both of those are analytic, nice, differentiable functions at 0. Okay. That means I can use the result we had yesterday. My buddy Frobenius, who said, yeah, you can write a power series that's going to look like this. It's going to work. At least one solution will work. The problem is that extra R is in there. And I need to figure out, according to Frobenius, I need to figure out the value of R before I can figure out the C's. So I got to start by figuring out what's going on here with R. But that means I need to put that into the differential equation. So I need y prime, I need y double prime. Because I know that R is a positive number, I hope, should be a positive number. All of my sums here will start at 0. None of them will be re-indexed. So let's take these three expressions, put them into the original differential equation at the top of the page. And then we're going to do a crap ton of algebra and try and turn it all into one big power series. So it's about to be a lot of messy, ugly algebra. All I did was copy in the sums where y prime, and y double prime are. I'm going to move the 4x in. I'm going to move the 1/2 in. These numbers right here. They're being multiplied in, so let's put them on the inside instead of the outside. That really doesn't do much to the second sum here with the 1/2. Just puts the 1/2 in front of the CN. But over there on the left, in the y double prime expression, what changes? In addition to moving the 4 in? Aha, because there's an extra x here. I add a power. And I didn't really change this last one at all. But now I notice something really nice. Even before I do anything else, I notice that both of these two sums here on the upper line, they have the same power of x. That n plus r minus 1 is the same in both of them. It means I can gather the terms. Those are the same thing. Glue them together and gather the coefficient. So really, now I get n equals 0 to infinity, 4cn n plus r, n plus r minus 1, plus 1/2 cn n plus r, all times x to the n plus r minus 1. And then I have the other one, cn x to the n plus r equals 0. That's gross. Yesterday, when we were dealing with series that were not caring about whether they were singular points or ordinary points, what did we do once we got here, where we had one series with one power of x and another series with another power of x?
I have a question for that. When you take derivative of this, I thought it would be like the first derivative would start at any one.
When we start with cn x to the n, then it's n x to the n minus 1, right?
Yeah.
And I know n is 0 the first time. But what happens here if you put in n equals 0? Do you get 0 here? I get r here. So I can't change and drop those off. Only in this case, I can't drop them off. That's why everything down here started at 0, because I couldn't do that. It would have been so much nicer, but that's what the difference is between ordinary points and singular points, is that I don't know enough to say I'm going to be able to throw some terms out. Okay. Now I'd ask my question again. What happens when I see one series with one power of x and another series with another power of x?
You put in K.
I have to do a substitution and reindex to make the power the same. I'm going to take the left sum, and I want to switch it so that this matches this. Really, I want the k to be n minus 1. Then this side will become k plus r. And here, I'll just change the letter to be k. So here, in this left sum, I'm going to let k be n minus 1. And in the right sum, I'm just going to change the letter. So what happens in the right sum is it just becomes k equals 0 to infinity, ck x to the k plus r. But what happens with all this over here? Well, wherever I see n minus 1, I'm going to put a k. So that means this will be x to the k plus r, because I have an n minus 1 on that power of x. But that also means wherever I see an n, I'm going to put a k plus 1, right? So what happens inside this set of parentheses now looks different. It's 4ck plus 1. And then n plus r becomes k plus 1 plus r. And n plus r minus 1, well, that's k plus r. And then I have plus 1 half ck plus 1. N plus r becomes k plus 1. And now I have a summation where k goes to infinity, but where does it start? It starts at -1 because k is n minus 1 and n started at 0, so k has to start at -1. Aw, crap. The sum on the left starts at -1. The sum on the right starts at 0. I want them to start at the same place. What can I do? Yeah?
Well, you plug in k equals -1 times 8. At the end of the equation, put k plus 1, but I think k plus 1 is hard for.
Yes, there should be a plus r there. Nice catch. 4, put in -1. 4c0 times r minus 1 plus 1 half c0 k plus 1 is 0 plus r. So there's an r there. X to the r minus 1. That would be what happens if I plug in -1. Yes? And then everything else now starts at 0. 4ck plus 1, k plus 1 plus r, k plus r, plus 1 half ck plus 1, k plus 1 plus r, close the parentheses, x to the k plus r, plus sum ck x to the k plus r. Whew. That's disgusting. All right. Technically, this can now all be combined, because that's starting at the same number, k equals 0, going to infinity, and they're both in terms of x to the k plus r. But I want to leave that for the moment. Let's start with the one extra piece. This piece for C0 R minus 1 plus 1/2 C0 R. Right? That's the coefficient for x to the r minus 1. This whole thing up here is equal to 0. What did we say had to happen if a power series was equal to 0? Not just the constant, the entire coefficient. So this whole thing has to be equal to 0. Let's simplify that for a second. I can factor out a C0. I can factor out an R. So if I take out C0R, what am I left with? Or that. I distribute the 4, right? This is called the index equation. But rather than use the word index, they take it, turn it into an adjective, the indicial equation, the thing about the indices. Screw it, it's the index equation, damn it. It's telling me about R. R is the index in question. That's why I call this the indicial equation, because it's telling me about R, and R is the index. It's the reason we have a pole. It's the reason Frobenius had to have this different looking series. I need this extra index. So far, so good? Effing weird, but okay. All right. So here's the deal. C0 is a free choice. Usually that goes with our initial conditions. C0 and C1 are going to be based on my initial conditions. That should still be true. So I want to look at this and I want to say, oh, the way to make this 0 is to look at the choices available for R. And the two options for R that work here are 0 and 7/8. So I have these two indices. And because I have these two indices and their difference is not an integer, I can now start to do things here. I promise there's a reason that we need the difference to not be an integer. I'll get back to it. But now that I have those two numbers, I have to find those before I can start finding the C's, right? I found the R's. Now I can start finding C's. How do I find C's again? Oh. Go back up to the original differential equation with the power series where I had the k-1 term pulled out. Back up to this giant thing. I dealt with this part where k was equal to -1. Now I have to deal with this part. So now I need all of this crap. Remember I said I can gather all that, but I was going to put that off. Let's gather it. I need you to write down the coefficient of x to the k plus r as one expression. Okay, I'll show you star. Let's put it all together into one giant pile. Well, the only thing that comes from the second part of this series is a CK. So I'm going to add that CK to all of this stuff. That's the giant ass coefficient, isn't it? What does that need to be equal to? 0. So now, again, as I said earlier, there is going to be some messy algebra. I need you to write this CK equals a bunch of stuff times CK. Oh, CK plus 1, right? I want the CK plus 1 all along. So I can tell you the next term is based on the previous one. Okay, wait a minute. These are CK plus 1. Matter of fact, there's a common factor of CK plus 1. There's a common factor of K plus R plus 1. K plus 1 plus R is the way I've written it here. So I have CK plus 1 times K plus 1 plus R times 4K plus R plus 1/2 plus CK equals 0. So now you can write CK plus 1 equals. What do you get?
negative CK. Bottom up. Okay.
Great. I love it. Wonderful. I don't like having a 1/2 in the bottom here. That makes me less than thrilled. So I think I'm going to cheat. And I'm going to multiply the top and bottom of this fraction by 2. And that makes it minus 2ck over k plus r plus 1, 8k plus 8r plus 1. I just brought the 2 into the second set of parentheses rather than into the first set. Do you see why I need to know the values of r first? My choice of ck now depends on which choice of r I use. And that means that there are 2 different power series. Remember, Frobenius' theorem says there's at least one. Since I have 2 choices of r, I get 2 series. The first one is what happens if I let r equal 0. If r equals 0, I can build the rest of this power series, can't I? R equals 0. That means that ck plus 1 is equal to negative 2 ck over k plus 1, 8k plus 1. And C0 is a free choice. Which means I could just as well let it be equal to 1. It's a free choice. I can let it be anything I want. If I let it be just C0, then every single term is going to be ending up written in C terms of C0. I'll just factor that C0 out front. And then it'll look like C times Y1. Oh, so just let it be 1 and make our lives easier. So if C0 is 1, what's C1? Plug it in. Minus 2C0 over k plus 1, 8k plus 1. Minus 2/9. Because C0 is 1. If I'm doing C1, then k plus 1 is 1. K is 0. That's why there's a C0 here. 0 plus 1. Oh, that's not right. That's a 1. I can do arithmetic, really. Sorry, people. Okay, now I do C2. That's negative 2C1 over 1 plus 1. Now there's my 9. I cross-listed my numbers here. And C3 equals, and I can keep going, right? I can go as far as you want. Negative 2C2 over 2 plus 1. 8 times 2 plus 1 is 17. So I get negative 2 times 2/9 over 51. Well, this is going to be disgusting. Negative 4 over 459. R was 0, right? So that means this power series is 1 minus 2x to the 1 plus r, but r is 0, plus 2/9 x to the 2 plus r, minus 4 over 459, x to the 3 plus r, but r is 0. Jack, if I'd left a C0 in all of these, there'd be a C0 there. There'd be a C0, a C0, a C0. I just factored out. I'd have C0 times Y1. So I really don't need the C0 to be any particular number. Aren't I going to get C1, Y1, C2, Y2? Oh, there you go. I don't need the number. Might as well let it be 1, make your life easy. But this is just one power series. What happens in the other case? What was the other R value I could use? Well then, CK plus 1 is minus 2CK over K plus R plus 1 times 8K plus 8R plus 1. Ew. All right, wait a minute. Simplify this thing in the right-hand set of parentheses. What happens here? Ah, well, now I'm looking at this and I'm going, that's really nice. But the problem is there's an over 8 here. So I'm going to factor an 8 out of this set of parentheses. And I'm going to multiply that 8 into the other set of parentheses. Oh, I rigged this mother so hard, everything works out in nice whole integers. What do I do now? I do the exact same thing. C0 is 1. Build the rest of it. That's nasty. It's right, but it's nasty. Okay, hang on a second. This now gives me another series. Jack, you're looking at it like it did something ugly till you talk to me. Okay. They're very different, aren't they? This one and the previous one.
Yeah.
As you say, I got the plus minus thing going on, so they're both alternating series.
Yeah.
But this second one, I start not with x to the 0, but I start with 1 x to the 0 plus 7/8. And then minus 2 over 15 x to the 1 plus 7/8 plus 2 over 345 x to the 2 plus 7/8 minus 4 over 32085 x to the 3 and 7/8. I'm going to factor the x to the 7/8 out. This is not a Taylor series. This is not a Laurent series. This is not a Maclaurin series. This is not a power series the way we like them because of that x to the 7/8. Where is x to the 7/8 defined? That's an algebra question, so you have to think back. It's an even root. It is only defined when x is greater than 0. That's exactly correct. But that means this whole function is only defined when x is strictly bigger than 0, a punctured interval. We don't get to use 0. We only get to use bigger than 0. Phew! I got two series. Only one of them looks like a traditional series. The other one doesn't. Because of that odd non-integer power of x, the other index, I did say my difference had to be non-integer. The two indices can't both be integers. They can't both be different from each other by an integer. So even if one was 1/2 and the other was 2.5, I'd be in trouble because they differ by an integer. Questions? Please note, I got the index equation by looking at the lowest possible power of x, right? I had x to the k was -1. That was the smallest I could make it. If x equals 0 is a regular singular point, then I take my differential equation. And if it's a regular singular point, multiplying by an extra x here makes it nice. Multiplying by an extra x squared here makes it nice. So I can actually change these if I multiply through by x squared. X squared y double prime. I'm going to write this as x times xp of x. That's multiplied by x squared. And then I'm going to write x squared q of x, y. This and this, those are analytic. They're nice. That's what it means to be a regular singular point. That means that xpx can be written as a power series. And that x squared qx is a power series. That's what being analytic means. I have a power series for both of these. Guess what? Our index equation needs those two numbers. You know what A0 and B0 are? Complex numbers, people. McNabb should have hammered this into your head. Those two numbers, A0 and B0, they're the residue of those two functions. Which means I can actually do this without going through that entire giant power series stuff if I multiply by x squared and the resulting expression is sufficiently nice. Here is a differently written differential equation. X squared y double prime plus 5/3 x plus x squared y prime minus 1/3 y equals 0. Look at the way I've written that expression that is now at the top of the screen. The p of x piece has an x factored out of it. I'm going to think of this as x squared y double prime plus x times 5/3 x, 5/3 plus x, y prime minus 1/3, well, plus negative 1/3 y. Guess what? Here's A0. Here's B0. My indices are the roots of this equation. No giant power series rewriting needed. Son of a... I saved my butt some work. R squared minus R plus 5/3 R minus 1/3 equals 0. That's going to be R squared plus 2/3 R minus 1/3 equals 0, which is R plus 1 R minus 1/3. There are my indices. Now, if I want to start finding the coefficients, I do need to do all the power series crap. But I short-circuited finding the indices. That makes my life a lot easier. Questions? In example 4, page 262, xy double prime plus y equals 0. Wait a minute. 0 is a singular point. P of x is 0. Q of x is 1. That means the two indices I get are 0 and 1. They differ by an integer. If we work out the power series answers, we only get one solution. That's the whole reason I need the indices to be differing by a non-integer value. If the two indices differ by an integer, I get the same series both times. And that fucks me over. But Frobenius only guaranteed me one series, so that's okay. Sometimes I get one, sometimes I get two. It depends on the integers. So I can't guarantee that I'm going to get two solutions. But if I get one, how do I get my second one? I've asked you this question before. Here is a solution to a differential equation. How do I get a second solution? I only use the initial conditions when I have two things I can plug in for, right? A C0, C1. But I only have, that means C0, Y1, C1, Y2. I need two solutions to do that. Back a couple chapters. If I have one solution, we can go through a process and find another. What's the process? That was for a particular solution for a non-homogeneous equation. I do variation of parameters or undetermined coefficient. It was before that. I use another method. Oh, son of a bitch. Wait a minute. Y2 equals Y1 times the integral of e to the integral minus P of x dx over Y1 squared. Oh man, that sucks. And the worst part about it is that I would have to have Y1 as a series, which means I have to do the long division to divide out the power series. Oh man. Can I do it? Absolutely. Do I want to? Hell no. Is it easy? No. Is it completely unacceptably difficult that we will never, ever, ever be able to? No, it's just ugly. Here. I end up with the integral of e to the x over x squared. I know a power series for e to the x. I'll just put in the one, and then I can integrate term by term. I know how to do this. Is it easy? Absolutely not. Is it doable? You bet your ass. Do I want you to do it by hand? No. I could do a lot more. I wish I had a whole nother semester of this stuff because there's so much more neat stuff coming. But this is it, people. You made it. So, chapter 6, sections 1, 2, and 3, chapter 8, section 4. That's what's due on Monday. Friday is question and answer day. I will answer any question you have regarding the homework or the exam on Friday or on Monday. All right? I will see you all then. Have a wonderful day.